All right. Jumping back in where we left off last time, we were talking about solubility, solutions, and recrystallization. In recrystallization, we're using that supersaturated solution. So we prepare a solution at an elevated temperature. We increase the temperature, that increases the solubility, like in this example with potassium chlorate. We prepare a solution at this elevated temperature, and we've got much higher solubility at this elevated temperature. Then when we slowly lower that temperature, we've got too much of our solute dissolved. Too much of this potassium chlorate is dissolved in the solution, and the solubility drops, and it crashes out of solution, or hopefully recrystallizes. Crashes out is a little bit more rapid, usually doesn't form nice crystals. At least that's how I put it together in my mind. And so when those crystals form, they form in a very specific arrangement depending on the conditions. But they form in a very particular arrangement that tends to exclude other things like water, and if there's other ions in there that aren't part of this potassium chlorate gang, those are going to get excluded from the crystals that are formed. And so this is one method that can be used for purifying solids if they're soluble in, for example, water. Gases also have a solubility relationship with temperature and some other factors. So solutions of gases and water are very common. Some of us maybe drink them every day. Fish depend on them to breathe. And temperature is one of the big factors that plays a role in solubility of gases when they're in water. The solubility of gases in liquids, unlike solids, decreases with increasing temperature. So as we crank up the temperature, we actually get lower solubility. So this is an opposite trend to solids dissolved in liquids. So a couple of the takeaways. Warm soda goes flat. That's one reason why you might put soda or carbonated grape-derived beverages in the fridge after they've been opened. It's so that the gases stay in there, they stay bubbly for longer. Oxygen levels are also lower in warm lakes and rivers. That presents a pretty big problem, especially if the water gets too warm. You can have fish just suddenly stop being able to breathe because there's no oxygen dissolved or not enough oxygen dissolved in the water. Or you get algae blooms or other things like that. This would be an experiment that you could try at home if you've got 2 cans of soda. Take some cold soda pop, a Midwestern author. Take some cold soda pop, pour it into a glass. Take some warm soda pop, pour it into a glass. Or just notice the difference. So if you like drinking your beverages really, really cold, you're going to get less of a bubbly experience. If they're warmer, they're going to bubble up more, so you're more at risk of getting spill all over the place. But you're also going to get a bubblier mouthfeel when you're drinking your warm soda or other carbonated beverages. One of the things that I like, or that I use to remember the way that solubility is related to temperature, if we take our states of matter and plot them on this very simple temperature single axis, we've got 3 states of matter. If we just take one thing, let's say it's water, at the lowest temperature, what phase are we going to have? What's our lowest temperature state for water? Solid. And what's a little bit higher energy than a solid? A liquid. And what's a little bit higher than a liquid? Gas. So for our solids, when we were increasing temperature, let's say that we start with something that's a solid. If we increase temperature, does that take us towards or away from being a liquid? It brings us more towards being a liquid. So increased temperature becomes more liquid-like. And our solubility increases. It gets along better maybe it's a little bit easier to break apart. On the other hand, if we've got a gas and we increase its temperature, does it become more or less like a liquid? Less. Becomes less like a liquid. It's more in the pure gas, or more gas-like, if we wanted to idealize it. So if we increase temperature, it's less like a liquid. Solubility decreases. That looks like SD decreases. On the other hand, if we cool down a gas, if we bring its temperature down, then that'll make it more like a liquid, and we would expect our solubility to increase as a result. So you're welcome to just memorize it, or you can use this as a memory tool. But when I thought of this, I thought, wow, that's really cool. So I'd like to share it with you. Another factor that affects solubility of gases and liquids is pressure. So the solubility of a gas also increases with increasing pressure of the gas above the liquid. The common example for this is a can of soda. Cans of soda, I believe, are pressurized to 2 atmospheres of CO2. And so when you've got a closed can of CO2, you've got a high pressure of CO2 in the headspace in this empty little bit above the actual soda. When you open up the can of CO2, that pressure drops suddenly. To about 1 atmosphere, depending on where you are in the world. And so now, because of that change in pressure, we've got a supersaturated solution, and so we're going to have gas bubbling out of solution. Similar to when we rapidly drop temperature with our solids. We can also increase the pressure of CO2, and that'll cause the gas to go into the liquid, so this would be the opposite process. We've got a cylinder with a movable piston, we've got some CO2 gas molecules, and we've got a carbonated drink probably. If we push this piston down, adding pressure to the system, that's increasing the pressure that these gas molecules experience, and that's going to force some of them to dissolve into the liquid. You could think of it as just there's no room for them, and so they have to go somewhere else, and the only other place for them to go is dissolving in the liquid. They're not all going to go into the liquid, but some of them will get forced into that situation. And then over time, that will equilibrate out, it'll settle, and then there's not going to be a net change in the amount that's dissolved. I've been seeing ads for nitrogenating. So carbonating is when you put CO2, and nitrogenating is when you add N2, nitrogen gas. Nitrogenating things that you can get at home that don't use any cartridges. The atmosphere is like 78% nitrogen. I think what they're doing is they just take a pump and they just pump lots of air in there, and since it's mostly nitrogen, it adds nitrogen to your drink, your beverage, whatever it is. And so you can make like nitro cold brew coffee at home. But they're like $500, so I'm not buying one. But that's like one application of this sort of concept somebody came up with. You could probably do it with like a bike pump and some good metal containers, but I'm not going to try it. A law that we have related to the effective pressure is Henry's law. One of a few gas laws that we'll get to deal with. So Henry's law, relatively simple. It quantifies the relationship between the solubility of the gas and the partial pressure of the gas. And we also have a constant in here. So S sub gas, S is solubility, usually in moles per liter or molarity. We've got K sub H, the K being a constant and H standing for Henry. So this is our Henry's law constant. These are things that you can look up for probably any gas that you can think of. And if there's not one that's published out there, then that's an opportunity. If you really wanted to, you could probably go find it and publish it yourself in a couple years. And then we also have P sub gas, which is the partial pressure of the gas. So the gas, whatever it is, the oxygen, the nitrogen, what that particular component's contribution is to the total pressure. The Henry's law constant is also temperature dependent, so this table is for 25 degrees Celsius. It's from the book. We can use this information, this S sub gas equals K sub H times the partial pressure of the gas, to calculate solubility. So let's do that for oxygen. Determine the solubility of oxygen in water at 25 Celsius, exposed to air at 1 atmosphere. Assume a partial pressure for oxygen of 0.21 atmospheres. Without ever having used it, give it a shot. All right, so the thing we're looking for the solubility of oxygen. That's going to be that S gas. And we're looking for that for water that's at 25 degrees Celsius exposed to air at 1 atmosphere. Assume the partial pressure of oxygen is 0.21 atmospheres. So we've got a K value, our Henry's law constant. We got that from the table. Hopefully we all figured that one out. We also have this P gas. We've got two different pressure values. Which of the pressure values are we using here? Yeah, we're going to use the 0.21 because that's the partial pressure for oxygen. Our gas is oxygen. So to find S gas, it's equal to our Henry's law constant, 1.3 times 10 to the minus 3 molar per atmosphere times the partial pressure of our gas, conveniently in atmospheres. The atmospheres cancel out, and we get 2.73, we'd round that to 2.7 times 10 to the minus 4 molar.
Is it going to be molar or molar over rate or something?
Yeah, same thing. Any questions about that? All right. When we're working with solutions, there's a lots of ways to express our concentration. We can do a qualitative description describing the qualities. Qualities. Like big. Big would be a qualitative descriptor. So our qualitative descriptions for solution concentrations are dilute, which would be low concentration, and concentrated, high concentration. These are relative terms, so there's like a little bit of wiggle room, a lot of wiggle room. So what I call a dilute solution for another chemist might be a concentrated solution, just given on the type of work that they do. For me, a concentrated solution might not be what another chemist considers to be a concentrated solution. So some wiggle room, but generally concentrated solutions kind of towards the higher end. In my mind, for things in lab, that's probably stuff that's above 1 molar, or at least in that range, and more dilute solutions are going to be like 1/10 of a molar or less. And then we have lots of quantitative measures of solution concentration, which are great for sharing information with other people, because when we're talking about a quantitative measure, quantitative, just stuff that uses numbers, like saying that I'm tall doesn't really give you an idea of how tall I am, especially since I'm sitting. I'm only 5'10", so I'm really not that tall, but I think I'm a little bit taller than average. So 5'10" would be quantitative, whereas tall would be qualitative. And for those of you who are actually tall, 5'10" might be kind of on the short side. So, it's all up to you. But quantitative, I can say that I'm 5'10", and you can't say that I'm wrong about that, because it's true. Some of our solution concentration terms are listed here. I say some of, because this isn't all of them, if you can believe it. So there's some of these, a few of these, hopefully, that are very familiar to us. The top couple, molarity, one of our best friends when we're talking about solutions. It's just moles over liters. We also have the very much less fun to say molality, which is moles per kilogram. And we've also probably done things like parts by mass, usually as a percentage. We can also do it as parts per million, parts per billion. There's also parts per trillion and parts per thousand, which get confusing because they both start with a T. And you can even go smaller than parts per trillion. And then there's also the very fun parts by volume, which is distinct from the parts by mass. And we're going to go into basically all of these. So the first one, hopefully you remember this. We've used it pretty extensively in chemistry up to this point. Molarity, it's the amount of our solute, the minority component or the solid, in moles over the volume of the solution. And we can use this to prepare solutions. For example, if we wanted to make a 1 molar sodium chloride solution, we'd weigh out 1 mole of sodium chloride, add it to a 1 liter volumetric flask, fill it up a little bit, get the salt dissolved, and then fill it up to our singular measuring line. Molarity also changes a little bit with temperature because volume changes with temperature. Just a little bit, so it's not a huge factor. But if you're using stuff that it really matters what molarity you have, it might become a problem. Some people like to use a little triangle thing when they're doing calculations with density. Density equals mass over volume. You can do the same trick for molarity. In my mind, though, I like to just sub in. I like to swap these two. If I see capital M, I know that I can just swap that in for moles over liters to get my units to work out if I need it to. Or if I end up with moles over liters, I'll just swap it over to the big capital M. And again, it's important that we use the capital M. It's distinct from the lowercase m, which we're going to see on the next slide. If you have questions, feel free to stop me at any point. All right, the one that's much less fun, in my opinion, is molality. This one is also the amount of solute in moles in the numerator. But the bottom is different. It's mass instead of volume. And it's solvent, not solution. So this one for me, because we didn't use it very much, always felt a little bit weird, always had a little bit of trouble remembering. And it also has to be in kilograms. Fortunately, if you're given units for these, sometimes it gives you all the units, so it tells you that it's moles in kilograms, and so you can work that out. Molality, unlike molarity, does not depend on temperature because the volume changed in the previous slide, but the mass of the solvent is not going to change with temperature. It might expand a little bit to change the volume, but it's still the same amount of mass, so we don't have to deal with any sort of temperature issues here. And this is the minuscule, or the lowercase m, for our symbol. And the reason that I like it less from a mouthfeel perspective is because that 1.50 lowercase m reads 1.50 or 1.5 molal. And I just don't like the way that molal feels in my mouth. So that's my personal grudge with that unit. Now on to some things that, getting towards some things that might be a little bit less familiar. A lot of times concentrations will be expressed instead by parts by mass. I think this is especially relevant in environmental science, especially when you've got very dilute amounts, very small amounts of contaminants in the environment. So a part by mass concentration is now mass both on the top and on the bottom. So what amount of the mass, what fraction, what percentage, what millionth, what billionth of the mass is solute. It's also really convenient because you can just weigh stuff out on a scale. You don't have to use a molar mass calculation. And then there's a multiplication factor. If we're doing percent by mass, the cent part means 100. So per 100, the percent by mass, mass of the solute over the mass of the solution, and we multiply by 100. And we've got calculations. We'll do some practice calculations with these. There's also another kind of similar to percent. So for percent, we've got the 0 over 0. If you've accidentally long held on your percent sign on your calculator on your phone or on your keyboard, I believe it's the 0 over 00. That's also a thing. I believe it's per meal. And the meal part there being 1,000. So this would be equivalent to parts per 1,000, which I'm told by reputable sources is ppth. That's one that we don't normally cover in the slides, but I think is worth mentioning because I think it's interesting. And then parts per million and parts per billion, which you'll often see if you're looking through again, like residues, water concentrations. If you look up the water quality report, there's certain things that the EPA has designated that public water has to test for, and so they'll put out a report every year or every however long that has information about how much of a thing is in your water. And usually it's perfectly fine. So the parts per million, it's the same idea as percent, but instead we're multiplying by 1 million. And for parts per billion, we multiply by 1 billion. And these are pretty, for a lot of chemicals of interest, these are pretty achievable limits or ranges for detecting analytes. Like our lab, we could probably detect chemicals at these concentrations, and you can certainly go lower than that. So you could go down to ppt, parts per trillion, if you wanted to. Possibly for some analytes, otherwise you'd spend a lot of money to get new instruments. So these are all using the same formula, just swap the last number. So all of the parts per, it's just a variation on a theme. And we can also do the same thing for parts by volume, which I believe is a lot less common. I certainly see it less. So generally, if you see a parts per whatever, you should assume that it's, I would assume that it's parts by mass rather than parts by volume. And all that's changing here is it's volume of the solute over volume of the solution instead of mass over mass. Questions about any of these parts? It's a pretty standard part list. All right, let's use some parts by mass and calculations. What mass of sucrose in grams is contained in 355 milliliters of a soft drink that is 11.5% sucrose by mass? Assume a density of 1.04 grams per milliliter. We are given a couple of things. A bunch of numbers might be relevant. We've got 355 milliliters of the soft drink. It's 11.5% sucrose by mass. We're also told that we've got this density value. All important information. And we are trying to find the mass of the sucrose. Another thing that we're going to need is our formula. So our percent is equal to mass solute over mass solution. That mass solute over mass solution, that's par for the course for our parts stuff. And what number are we going to use for percent? 100. So if we are looking for mass of sucrose, the sucrose is our solute. We're looking for the numerator on the right side. We were given our percent. Were we given our mass of solution? We were not directly given mass of solution, but we can find it. So we can find the mass of our solution because we have volume and density. The units tell us to multiply. So 355 milliliters of soft drink. What mass of soft drink is that? If we multiply by 1.04 grams per milliliter, for those of you that are new to taking my chemistry classes, I like to write things separated in the numerator, the denominator, so I'll write a long line across the middle, and then we separate out the things we're multiplying with vertical lines. And that makes it easy to keep track of where our terms are and what's on top and what's on bottom. And then we can cancel things out that show up in both spaces. So the milliliters cancel out. The unit that we're left with is grams. Do 355 times 1.04. $369.2 grams for the mass of our solution. So now in this original equation, we've got the percent, we've got the mass of solution, 100's already given to us. We only have one variable left, that's the mass of the solute, and that's what we want. We can solve for that variable. We'll just have to do some rearrangement. Okay, so we rearrange. We get mass solute equals mass solution times percent divided by 100. So we put our 369.2 grams times our 11.5% divide by 100, and that'll give us our answer. So in this soda, we have 42.5 grams of sucrose. Questions? All right, one for you to try. A water sample is found to contain the pollutant chlorobenzene with a concentration of 15 ppb by mass. What volume of this water contains 5 times 10 to the 2 milligrams of chlorobenzene? Assume a density of 1 gram per milliliter. Just as a reminder, ppb is parts per billion. So identify what you're given, identify what you're looking for, write out an equation, figure out what parts you're missing. There's also some unit changes, and we'll come back in a couple minutes. All right, so I wrote out kind of partway through, most of the way through. This is the equation that we're dealing with. ppb equals mass solute over mass solution times 10 to the 9. The ppb and the 10 to the 9, the only things that are different from this percent one that we used earlier, where we had percent and 100 instead of ppb and 10 to the 9. But this is the one that we're using here. We're given some information in the problem. We're also given some flavor text. So the important parts are 15 ppb. The by mass is helpful, since we also know that we can do it by volume. And our pollutant or our chemical that we're talking about here is chlorobenzene. So 15 parts per billion chlorobenzene. We are looking for volume of water. And related to that volume of water, 500 milligrams of chlorobenzene. So the 15 ppb slots in that ppb area. And the 5 times 10 to the 2 milligrams chlorobenzene fits in up top, since chlorobenzene is our solute. What's the solvent in this situation? Water. The liquid or the majority component. So we've got ppb, we've got mass of the solute, we can find mass of the solution. That doesn't directly solve our problem because we're looking for volume, but we do have a density that'll let us convert mass of solution to volume of solution. So we will rearrange. Going to multiply both sides by mass solution. And I'm going to shorten to M solute. And we also still have our 10 to the 9. So that M solution, just moving our mass of solution, and then we have to also move our ppb. So mass of solution is equal to the mass of the solute times a billion divided by parts per billion. It would also be helpful to convert at some point this milligrams. And the reason that I say that is we have milligrams here, but we've got grams in our density, so we'll need to convert it or we'll end up with the wrong answer. I'll go ahead and do the conversion up front. So that'll turn into 0.500 grams through the power of having used a lot of metric prefixes. We all tracking so far? Okay, so our mass of our solute, 0.500 grams times 10 to the 9 divided by 15 ppb. And we get a very large number. .3 repeating times 10 to the 8 grams. chemical identifier here would be solution. And then we can just magically convert that to milliliters. I say magically because we've got 1 gram per milliliter, so we can just, those units are interchangeable effectively. Question?
7 to the power of 7. Is it 10?
Oh, yeah. I screwed up. Nice. It is to the 7. I made the classic blunder. The classic blunder being I wrote times 10 E7, the little capital E. Classic blunder. All right. That's the correct answer. Questions? So one way that we could check mentally, is this a reasonable answer? We have a very low concentration. 15 ppb is a very small concentration of chlorobenzene. We're looking for half a gram of chlorobenzene. If we have a really low concentration and we're looking for half a gram, that's a relatively large amount. We're going to need a really, really large volume, and we got a really, really large volume. If we had gotten a really small volume, that if we've worked with concentrations and masses a little bit, that will hopefully set off some alarm bells. So that's one check that's going through my head when we're doing this problem. Other things that we can use are mole fraction and mole percent. So the mole fraction we use, I believe it's chi. Looks like chi, the Greek letter chi, is often what we use for fraction. So chi subsolute expresses our concentration as the amount of our solute in moles over the amount of our solution in moles, or solute plus solvent in moles. And we can also express this with just symbols, where N stands in for moles. So what fraction of our total moles is solute? Is basically what this, the question that this gives us the answer to. Is it half? Is it a quarter? Is it a third? Is it smaller or bigger than that? Fraction's a little bit weird because usually we just go ahead and express it as mole percent, where we multiply things by 100%. So our mole percent is just the fraction times the 100%. And if you wanted to, you could just tack that 100% on at the end of this formula and swap out our fraction with mole percent. We have a solution prepared by dissolving 50.4 grams of sucrose in that many kilograms of water. The final volume of the solution is 355 milliliters. Calculate the concentration of the solution in each of these units. I'll give you a couple minutes. Feel free to ask questions along the way. And I'll add some helpful hints. couple of things that we're going to want to do. It seems like maybe we're getting to the point of being close to being done, if my read is correct. So a couple of things that we're going to want to do to make our lives easier. We're going to need moles for both our sucrose and our water. So it might help to just go ahead and calculate those right out the gate. So 50.4 grams divided by our molar mass. And we've got approximately that many moles of sucrose. We can do the same thing for our water, 332 grams divided by about 18. We've got 18.429 ... moles H2O. I use the ... to indicate there's more decimals there. I just don't want to write them, but acknowledging that they're there, and I'm going to use them in calculations so we don't get rounding errors. For molarity, molarity is equal to moles solute over liters of solution. So we're going to take our 0.1472 ... moles sucrose, divide by 0.355 liters. That's the volume of our final solution, just converted to liters. And we should get a value of 0.41, round up to 5, molar for our molarity. For our mole fraction, we're going to be using that 0.47 ... moles sucrose over the same number plus our 18.4 ... moles H2O. This is where it really comes in handy to be able to just recall those numbers from earlier entries in your calculator. And the number I'm getting here is 0.00793 for our mole fraction. Our label maybe here would be sucrose. For our molality, we're using moles sucrose, since that's our solute, over kilograms solvent. Conveniently, we were provided with in the problem. So the moles of sucrose, again, that 0.147 number. Dividing by the 0.332 kilograms of water that we were given in the problem. And our molality, 0.443 molol sucrose. Any questions so far? for mole percent, we're taking our mole fraction and multiplying by 100%. So it's 0.793% sucrose. And last but not least, our percent by mass are 50.4 grams sucrose over the mass of the solution. I don't know why Siri keeps popping up. And it's a percent, so we're going to multiply by 100. And we get 13.2%. Also sucrose. Questions about any of these very fun calculations? All right, that'll do it for this installment of Chapter 14.